Hi, I don't know whether there's anyone there, probably not yet, but hey, um, it's just a talk really about some rather wild things that I found in the over a long time, really. I mean, I looked at the things that were related to this at a PhD level back in 1997 with Professor Noel Baker. And actually, we rather like string theory is a theory that has fallen backwards in time. The line that we were taking is actually more advanced than where I got to at the moment with it. And but it does indicate the way forward. And it's got a lot of peculiarities about it, the theory. It's largely identical to standard quantum theory, field theory, which it basically has to be because quantum field theory is so accurate. The anomalous magnetic moment of the electron is known to extraordinary precision. And the advance in theory since quantum mechanics started has really been quite staggering. But strangely, a lot of these ideas go back right to the beginning. And in the if we think a little bit about the history of field theories from Newton onwards, there's always been a tension between scales. What scales do theories work at? What scales do theories not work at? And that's led very much nowadays to the notion of an effective field theory. And that subject is extraordinarily advanced nowadays, to the extent where we can write down the mid-band quantum gravity, basically. And the equations that I recommend anyone to look at for the gravitational potential in essentially any compatible quantum gravity theory, there's always going to look the same. And we know enough about quantum field theories to know that if an effective field theory says this is what the answer is, it's probably correct at that energy scale. And it will even give us ideas about where it will fail, and we have asymptotic freedom and asymptotic safety, which give us huge amounts of information about the running of parameters. So really, quantum field theory has got far further than it was even in the 90s when I was studying it or beginning to study it with Noel Baker, before sadly he died. And when he looked at the equations, he wrote back and he said, oh my God, this does seem to work. So, but actually there was still a lot to go. So who knows what he'd seen in those early scribblings. But so where to start, really? Probably at the places where Einstein is probably a pretty good place to start, because he always had a very valid criticism of the quantum mechanics at the time, which was he was quite resolute. The field equation should be determined by quantum number, and that's it. No other parameters. And general relativity just places really harsh conditions on the gauge group. We're given a diffeomorphic. Let's forget the easy, grossly asymmetric gauge group of the standard model, which is chiral, and instead be more aghast at the fact that the gauge group of general relativity is a diffeomorphism group, which is just infinite dimensional. There's not much we can do about that. And so we're stuck with these constraints, and if we do want to look for a general a covariant theory of quantum mechanics, it has to essentially be deterministic. We have no choice if it's going to be compatible with general relativity. But then at the same time, we know that the theory has to be highly non-local. There's no doubt about that nowadays either. The information theory is quite resolute. The non-locality is just built into the theory, and and in fact we can quantify that to some extent. Well, almost exactly. So the firewall paradox through a bolt. Just threw a stick into the standard reasonings about black holes. Something had to give, and the most obvious thing is locality. And so we know Bell's inequality is violated by the Tirelson bound 2√2, and but very interestingly, it's been shown that that is only the case if the one or other or both of the tests are too correlated. So it's essentially relying on the randomness of choices, which essentially we're told by determinism are correlated to the measurements. But essentially, if one party just goes, I'm just going to stick to choice 0, then the correlations break. And this has been tested by Aharonov, who surely has been one of the most revolutionary, if misunderstood, physicists. Now, this is probably the best place to start, actually, because it was his birthday recently, and happy birthday, Yakir. And I have to say, your talks are inspiring, and particularly recently, where you were asked which picture you prefer. A weak reality or a path integral based reality of the sort conceived of by Feynman. And you gave the answer that, well, that is how you compute things. I would disagree. Feynman's system, although it is extremely insightful and useful conceptually, also contains an enormous mistake, which is shown by the vacuum expectation calculations, which are hundreds of orders of magnitude out. So, on the other hand, the picture you give is very simple, but also extraordinarily difficult for someone to understand what's going on. And the problems are this, basically. Quantum field theory is fundamentally, and general relativity are fundamentally topological. Yes, there's a lot of field content in them, but if you can solve the topological problems, the rest of the problems are difficult, sometimes non-locally non-solvable, and certainly the holographic equations show every sign of being in a class of extraordinarily difficult equations, elliptical equations, of exactly the sort that I was looking at in Baker. And so we essentially went straight in and solved the holographic map to some extent without realizing it. But it's not a useful solution. Yes, you can write down the Beltrami equation, which is what it's all based on, where essentially we allow the complex structure to vary across the orbifold. And so this sets up, that's it basically. It's just the Beltrami equations, but to anyone who's studied quasi-conformal analysis, this is no easy task. They're tremendously powerful tools, or it's a tremendously powerful tool, but at the same time, finding solutions, even though we've got essentially surfaces of no back reaction and event horizons everywhere like a fire. It's still going to be very hard to solve, however the Beltrami equations are actually derived from it. It's kind of knowing the trick before the exact implementation. But basically the Higgs field is the measurable dilation equations that you use to vary the complex structure over the orbifold. And then for any string theorist, there should be, just like, So this enormously cuts down on the phase space for string theory. But obviously then the thing is even if we've got the Beltrami equation and we've got all this stuff, and we need to look at the overall qualitative behavior of the topology, and this gets extraordinarily difficult. Basically, the beginning of it is easy in theory. We want a compactified time. Now, this immediately means we get left and right moving. Well, also we want to make a cyclic universe. So that means we're going to compactify it on a circle. And so we're going to compactify time. And then we've got some kind of spatial bundle to wrap up, to wrap that. We're essentially going to use what is quite a modern idea of using an external clock. And this is going to be an absolute clock. So it's essentially on a light plane. So and that time, because it's absolute, can easily be quantized. And so it makes for a situation where certainly the early low dimensional cases are actually very easy to compute on a computer. It's very fast. And so the algorithms are extraordinarily efficient. And well, they kind of have to be, because the universe is, as we'd imagine, maximally efficient. In fact, if you look at it, the equations for general relativity, just looking at the time dilation component of the tensor, the metric tensor, is essentially talking about how to design a perfect quantum computer. And so indeed, we'll see that the perfect quantum computer essentially would use no energy. And that's what this does. This system essentially just borrows and returns energy and does no work. So it's an isoentropic process. This means that it is a collapsing universe. So it has an expanding phase and a contracting phase. Loads of the things are called constant, in the absolute frame of reference, the cosmological constant is precisely zero. But in the forwards time sector, that can be both positive or negative. There exist times, even positive. So it is possible to be aware in a contracting universe, but in the opposite pockets, which is strange. So we have what's key to making a time symmetric universe, even though it's got so many strange asymmetries about it, is that we're relying on the no signaling theorem to mean that we can only be consciously aware in a region where time is increasing. So time is where curvature is positive. And so when curvature is negative, then the time is going to be decreasing, and there's no computation possible, no consciousness, no signaling possible in such a universe. But in that typical way of complementarity, there are other things that you can do in a space of negative curvature, as is well known in using all the incredible techniques of Malvasena. Now, it's in a way, the funny thing was when I did the analysis on the Beltrami equation, I was, after Noel died, I looked at it a bit more. And even though I hadn't found the framework to explain it fully, I still came to the conclusion that it was non-local but deterministic, because we had a deterministic equation, Beltrami equation, and so that's kind of led me to abandon this whole line, really, because quantum field theories and probabilistic theories are really where it's at, was really where it's been at, and being deterministic theories have been extremely out of fashion, there's no doubt about it. But Sabine Hoffenfelder's very good YouTube on superdeterminism kind of rekindled a spark. And in fact, a lot of these ideas I wrote up on there, some huge mistakes, some things virtually identical to the current theory. And so since then, I've been really just scratching up on quantum field theory, because really, to be honest, even though I found the Schwartz-Green-Witten book mind-blowing, but also mind-blowingly difficult, the first and second quantization just seemed alien. And although it made some kind of sense to me, I was coming from a very different perspective of transcendental entire functions and complex dynamics. So it can really, really very, very different discipline. And even though it had been something I've been interested in since a teenager, it never really made full sense. And I knew there was something, everyone knew there was something wrong about it. So I was more interested in looking at issues only indirectly related to these things. But one of them has been quantum computing. And I created a quantum computer language in 1991 that was really quite different from anything that's been there or since, and at some time I'll release it. But it had some very strange properties. Then it turns out it's related to a lot of things that Penrose has done, category theories, all these kinds of things. Monoids, and in particular, Gödel's theorem. Now, Gödel's theorem is a pathological mathematical result. It can't be proved by a computer. It can't even be checked by a computer. Which puts it in a class that I suppose Penrose would say it's essentially transcendental. And if you can, it's a bit like quantum mechanics itself, that if you can understand what Gödel's theorem is talking about, you have transcended axiomatics itself. And so it's very important to understand what Gödel's proof is saying, because it's very ill understood. What it's saying fundamentally is, you can, given any axiomatic system, it's actually pretty easy to write a proof checker, something that just checks whether, if this thing is a hypothesis, is this number the Gödel number of a proof? And kind of the first half of Gödel's paper constructs this function Bavecki. And then he coins it. he feeds Bavarian back a pre-prepared state that essentially induces what in quantum mechanics would be now called a frustrated quantum state. It can't even be answered in quantum mechanics. That's the point. To really, it can't be. You can't extend it, even if you add extensions to PA, to piano arithmetic. You still, and so you like say, all right, I've found this bad Gödel statement. Let's try and cut it out of the logic. You're done. You can check every proof up till the first Gödel number, but that sets a hard limit to complexity. Above that limit, you are out of a Heiting algebra and you're into the Wild West. Now, this might not sound important, but if you think about quantum computing, how do we say whether a quantum program halts or not? Now, if you look at a traditional programming language, it's quite easy. You say, well, it's an eigenvector of a vowel. So then we just jump to the same conclusion. Well, every computable value, if we want to treat a quantum computer as something that we can get answers out of, then eventually we'd have to do a hard observation on it. And that is essentially checking for an eigenvalue of a Hamiltonian. So that means we can say, we can identify non-halting quantum processes as precisely those processes which are not eigenfunctions of the Hermitian. And so essentially what we're saying there is the simplest one for that would be a spin reversal. Because then every fermion we put in spin up is going to pop out spin down, and it's not an eigenfunction. And so that process of spin rotation, if we were to implement it, spin flipping, is essentially an eternal quantum computer, because it's the quantum computer equivalent of Gödel's proof. So that instantly sets a complexity, a minimum complexity to the theory that has to construct it, i.e. we have to be able to, if we want to do this really properly, then we have to look at the minimum amount of information required to specify such a system, and that has to be above, well, we can assume, knowing the universe, it's exactly on the Gödel, so it's the first Gödel statement that the quantum computer runs into, or one of them. But if it's counting through in order, it's going to be the first. It's going to throw all its resources it's got to try and solve it, but it never can solve it within that quantum algebra, so it's just going to be like a fractal. Now, so we can think of the various iterations that such a computer would attempt to do to solve a Gödel's problem. And so that immediately tells us we're going to have a little bit of fun constructing the correct manifold to do the as our vacuum state, because that has to correspond to the smallest Gödel number within that particular system. But we can take some, that's going to help us find it. And we can certainly pin down some very good first guesses as to what it is. Because, first of all, we know it has to be an orbifold. It can't be manifold. We know it's non-oriented too, because it has to every flip, every rotation, it has to be non-halting. So it has to be essentially fermionic. That's a topological solution. That's going to result in its non-orientability. And essentially, we can draw the corollary that a bosonic solution is halting. So, which is a bit peculiar and needs further interpretation because it's kind of like the opposite of what you'd expect. But being, rigidly applying quantum information principles, it's what is derived. So, that's the case of shut up and compute. Now, so we know that the fermionic solutions have to be non-oriented. They both have singularities in them, both the bosonic and the fermionic solutions. Now, in the notes that I put for this, I wrote, and obviously, obviously, the bosonic solution is unstable. And so is essentially just a virtual particle. All the bosons are essentially virtual particles. And so that has to be considered. And it relates to many other intricacies in the system. The other thing is it will fit pretty well any chiral quantum field theory. You can plug this in, but there is, again, a very peculiar, something I really didn't expect. And it is essentially, I just found this today, and it's why I'm making this video, because it's just so strange. Because it comes from the fact that, right, well, first of all, this we have to kind of bootstrap stuff. We bootstrap observables, and this is using the Aharonov method. So something related to the ideas of Aharonov anyway. The notion is, okay, so we compactify time, and we imagine that we've got, for the moment, let's just have a creation operator. And we imagine the vacuum decay. Now, that vacuum decay is going to produce two particles, excitations, with opposite quantum numbers. Everything is reversed. Now, apart from, of course, spin zero, which is fixed. So that makes spin zero, the spin zero field, very, very, very important, because it is essentially the vacuum state. And obviously, what we have to do, we're kind of forced in our first stages. We have to let this thing run the Schrodinger equation. Everything has to run at the speed of light. Electrons the works. Okay, technically there are tricks you can do. But the notion is we really do want these fields to move, all the fields to move at the speed of light, because if we think about it, it's like the difference between an electron and the Coulomb field. That an electron doesn't need to move at the speed of the Coulomb field. So the Coulomb field is moving, propagating through an empty. If we imagine just putting the creation operator in, just to imagine it, just putting it for the moment in an empty Euclidean space. So we haven't got even a Minkowski space-time yet. That's emergent in the bubble. Now, so we've got the Euclidean metric in this, so basically a flat space-time, and that's what the nice part of this, from the point of view of effective field theory. You always want to be doing non-perturbative expansions from the vacuum state. And so here we're just starting with a flat space. So it's great, no problems. And we can quantize it later if we really want to. And certainly for computational purposes, that's very useful. And obviously, then we just run into the discrete Fourier transform rather than the continuous Fourier transform, just in details. And in fact, de Hooft is looking at just this kind of idea at the moment. And so we've got this nice Euclidean time axis, and then we've got to kind of couple it with something that's going to become the spacey dimensions. And we've got a few choices, really. All right, so let's just think about it for the moment in Euclidean space. And we have this creation operator. It's created basically a light cone spreading out in in the many dimensions we want it to spread out in. And then it's not going to really do anything if it's a Euclidean space, because it's just a wave function. So if we could say it represents something, it's some kind of multiverse. And so, as Aharonov says, and as Hawking, and this idea runs back and back and back and back and back, that if you can fix the initial and final conditions of a quantum system, it actually becomes classical. And so what we can do here is essentially interfere the Schrodinger wave with itself by compactifying time. So what that does is it just splits it into left and right moving modes, just like we're used to doing on a closed string. And we get a light cone spreading out from each of these sources. So there are two light cones. And they're going to intersect and interfere at some stage. But this is the beauty of where Aharonov had really seen ahead. Because the thing is that outside of these light cones, the field strengths are actually zero. So we can cut off we just need the intersection between these two light cones. So now it's really just a choice of the dimensions that we use in the space time in the space-like bundle, and there the most immediate thing is to say, well, just make it, 3 space. That gives you 3 space for 1 time dimension. But I don't know. I don't think that works very well. First of all, it doesn't really tally with what we see from effective field theory, which is essentially a 5-dimensional theory. So the natural thing to do is to use S5, and so we've got 1 compactified time dimension and a kind of twisted intersection of light cones. And they're twisted because we need them to be twisted at the singularity, and then we want the antimatter wave to completely annihilate the forward time wave at t equals half. Right here, I'm just using t equals 0 and 1 as the endpoints for the periodicity. Much easier, just like 't Hooft is strange. It's exactly what I do too, and I have done for ages. And again, just like 't Hooft, the action of a black hole is a CPM-T reversal. And we can see that this is all absolutely consistent between the models. The thing is with if you have the 't Hooft CPTEM going to the same sector, then you got big problems. So the notion is that, well, we've naturally got 2 sectors, a time reverse sector and a forward time sector. So instead of what 't Hooft was doing was entangling the black hole with itself, with its own antipode. But here we kind of do an antipodal map between the 2 spheres in the 2 spaces. And we can see there's actually a few ways we can do this. It's not absolute, it doesn't seem to be completely pinned down. You can allow for a couple of different possibilities, and they do give different models, but once you've chosen those parameters, it does appear to be fixed. And this was what I was kind of looking at really on the superdeterminism thread, where this has to do with electrons, because the problem is, all right, so I think, all right, so basically the most flexible model seems to be to use S5, because then we get an 11-dimensional theory, and that gives us a really, really broad number of particles. So it essentially gives us a potential physical model for M theory if we're using the 11-dimensional model. so there we've got essentially the circle, which we could think of as just a double copy anyway of two gluons. And then we've got essentially these, let's call it A10. It's a kind of A5 with some twisted product of A5. So it's got properties of a projective space. It's got properties. It's non-oriented. It's an orbifold. It's really a wonderful thing. And I was quite surprised it wasn't what a twister was when I looked at twister theory, because I thought it must be up Roger Penrose's street. This thing, it must be something he's looked at. So apologies if you've done it before, but it's certainly nothing I could find. And non-oriented orbifolds just seem to be something that have not even first, and everything's oriented, everything, and so it's a bit of a kind of Wild West. A lot of the theory breaks down. At least we can kind of cut it into oriented sections, and so essentially, even though it is not orientated, it doesn't seem to be a big deal, and it essentially comes down to fixing the gauge groups when you're crossing event horizons or going through singularities. And that's the other important thing. The singularity is an absolutely critical part of the theory. It just like in 't Hooft, it's a central, like the central point of a projective plane. If you don't, that's where you're putting your interaction operators. So it's not a bad singularity at all, because it's just like the center of a projective plane. It's just the thing everything goes through. And they're just rays, so there are just like dualistic theories where we can talk about rays and projective spaces rather than necessarily talking about point-like particles. So it's not really a big deal that there's a singularity, and from the point of view of holomorphic functions, well, it's all dependent on zeros and poles. So we need poles. And in fact, they are the annihilation and creation operators. That's the other thing about these time symmetric theories, and there are a whole bunch of them, is that essentially you don't need to make the difference between an annihilation and creation operator. They're just time reversals of each other. And so that just, again, the degrees of freedom drop out all over the place. And the most importantly with the Higgs, I mean, this is the thing that I'm just trying to get my head around at the moment. There are still open problems, obviously. I mean, this is the most enormous topic, but at least this gives some kind of way of patching up the horrendous issues with the cosmological constant and bringing it back down to scale, and keeping most of QFT intact at the same time. In fact, I'm trying to find what changes, and as you can tell, we don't even need to get the gauge group absolutely pinned down, or the qualitative notion that we just have some kind of spin reversal is enough. And then the thing that I've been checking out, because obviously I wouldn't want to make any public broadcast about anything like this, things just didn't add up, and the basic ideas just click together in some kind of consistent way. And obviously the most important thing is the coupling of the Higgs. How does the Higgs in this theory couple with what the Higgs field is meant to be in something like the standard model? And there's one slight difference, and I couldn't immediately see whether there's any obvious way of not doing this, which is that we can, the Higgs in the standard model, the Higgs field, consists of a psi plus and a psi zero, two complex scalars, but we've only got one, which is the weak product, because we've only got one. There's nothing really to unless we can make some kind of weak product of subfields. Now that's a possibility. The problem comes down to this: is that can we get charge on an event horizon? And if we can't get the psi plus in there, we can only get, now let me just check, it is the weak hypercharge. So my guess is that we do need charged black holes, in which case we're going to have to find some Bargmann invariant, a weak invariant, for measuring the sigma plus Higgs scalar. Now the thing is, we just don't have any degrees of freedom, so it's got to be a derived value. The sigma naught seem to fall out quite naturally, but I think it's deeper to find the sigma plus, and if there isn't, it's not, well, it could be a problem. The problem occurs is, can we drop electrons into a black hole without a balancing positron? And well, it just falls into a hole. This is one part of the theory that is particularly difficult, because we do have a little bit of choice of gauge groups remaining. And so this has all got to do with matter antimatter imbalance, because rather than having matter and antimatter, we've actually got four things. We've got matter, antimatter, and then their reverse time counterparts. So essentially we've got a real, since we can find positrons and they have positive mass, we want to take one of the particles in the negative sector and find a mechanism to swap it out for the negative energy positron, which obviously has to get quickly annihilated by something. And well, not necessarily quickly, but tunneled away. As Aharonov has actually done experiments in this. It's the now famous disappearing electron. And so we've seen it happen. I mean, this can be done in a lab. So essentially, there are a few lab experiments to do here to actually try and pin down. Like the mysterious top mass is exactly twice the other masses. That just seems really peculiar. If you've got a shadow sector, then you could easily imagine adding two of those masses together and like getting a top mass that's like the mixes of the two sectors. And likewise, we can, well, by tweaking the positron conditions, we can actually essentially fine tune the baryon imbalance by specifying that, you know, the positron and the forward time positron and the forward time electron fields are out of balance. But we have to have some kind of symmetry breaking to remove real positrons. The other thing is there might be some kind of mixing factor. There are a whole bunch of ways that this can be done, and I was actually this is going right into the kind of trying to get into the nitty gritty details about the missing symmetries between the symmetries between the our sector and the dark sector. But the interesting thing is we kind of know they all have to be weak. So essentially everything has to be constructed out of weak observations, unless we're on the place where the real part of the Higgs, of the psi zero component of the Higgs is zero, because that's really what you call the bones, the skeleton of the space, because you can't. It's analytically much easier to look at this space because it's Euclid, it's flat, so it's not curved. Well, at least time in its local geometry, it's flat. So and it's quantized in area with you know, the square of the Planck, also the Planck area, and obviously that's getting into the holographics of it all. But this is a surface that you do holographics on. That's the thing, because it's a rigid surface. There's no back reaction on it, and so that's what you need to do holography on. You need something that's got no back reaction, and then at the same time you expect for quasi-conformal solutions within the bulk. Essentially, we're going to be setting up Beltrami equations, and they're just, you know, measurable. So we've got the measurable Riemann mapping theorem behind us. So it's a very, very powerful theorem, and that guarantees the existence of solutions in these cases, as long as, you know, we can immediately just make the assumption that the psi plus field, the psi zero field is complex dilatations, and then we've made contact with quasi-conformal analysis. I essentially know less about the psi plus field, and obviously that's still work in progress. What does seem interesting is this surface, the event horizon surfaces, and maybe now it's time to get into holography, because, all right, so we've got some kind of outline as to how to actually create the holographic maps, but it's very rough. But there's with the now I've slightly lost my thread here. It's so difficult. Pardon me, I'll just have a sip of water. So we're looking at holography, yeah. So holography is the most interesting thing here, because I think I'm getting to the stage where my concentration is fading a bit. But it was really holography that was my way into decoding some of the finer details of this, and in particular, the fact that if you just write down every single equation that you can about event horizons and Hawking temperature, and you find that acceleration is quantized, and this is just very peculiar. But you also find that essentially the temperature is related. So the temperature of the event horizon is related to all sorts of things. And in particular, you can use it as, well, the ultimate particle accelerator. And so, which is a bit peculiar, because you'd imagine you couldn't, but you can. And the idea is this, is what we want to do is we want to get a microscope and zoom into any scale we want. And so how do we do this? Well, the fact is this, that if you're zooming into higher temperatures, that's a higher energy scale, obviously. But energy scale and temperature is just a higher temperature. And so as the temperature rises, the event horizon shrinks. And it's just the same with the Rindler horizon. This is how you get to it. So it's almost like the universality of event horizons, that it doesn't seem to matter what space you're in, you still get these thermodynamic relations, and they're all the same. And so the fact that they're all the same, well, it's the same here too. And so that means, okay, let's just turn it up to the max. Oh, zoom it up way past, what you fancy. It doesn't really matter. The point is this, is that the unrow temperature is going to go up and up and up and up and up. And the Hilbert space, the dimension of the Hilbert space, is just E to the partition factor. So it's a dimension. The Hilbert space, the dimension of the Hilbert space keeps on shrinking down to E to the 0, which is 1. A one-dimensional Hilbert space. And what's a one-dimensional Hilbert space? Well, it's almost nothing. It's one classical bit. It's not even a qubit. It's one classical bit. And so what do we get when we turn up the unrow? I mean, so we turn up the mass scale, the energy scale to the max, and we find one classical bit in baking in unrow radiation, and we go up even higher, just find that the hotter and hotter and hotter is still one bit of information. So what is that one bit of information? Well, it's obviously, are you looking at an event horizon or not? So essentially, and that's only to be expected, and it's always also to be expected when if you blast it up to any energy scale, the answer to me, yeah, you're looking at an event horizon. So it's not really, it's not really that. It is useful, but it isn't. It is useful because it's just telling us that we're just looking at the space where we can make observations. So, but at the same time, it's quite interesting to see that fundamentally everything can actually be derived from a tensor product from all of these spaces and the topology. So, I mean, maybe it's not going to be the smallest Gödel number that we're going to find, because it looks to me like that is crazily efficient. But that's how nature is. But at least we know now and don't need to essentially waste loads and loads of money on building a particle accelerator that's bigger than the universe. And so what to conclude from this? It's work in progress, there's no doubt. I haven't even got the relativistic formula for vacuum energy, because remember, this is all done in essentially the external clock gauge, so which is a universal time, and there's a bulk time too, but as you can see, everything is much more complicated than the bulk. Qualitative solutions are expected, and the equations are nonlinear, horribly nonlinear, and the behavior is non-local. That's the really important thing. So wherever we are on an event horizon of some sort, then that's essentially the only part. First of all, that's the only place where we can make any observations, actual strong observations. So, which is a bit of local observations, and we're only ever making them in the bulk too. So they're always going to be, approximate, and there's just so much intricacy to do with the holography on surfaces like this. I mean, where to start, really? I suppose what I'm going to look at next is this sigma plus field, and finding out whether there's a way to integrate that, and also looking to pin down the gauge symmetries to ensure that we're getting twists of the right kind when the spins go through a cycle. In fact, previously I was actually using the Galois fields to do this, because it's almost easier than using normal complex fields, and then they're discrete. So there's lots of possibilities. However, they're not very good for other things. So it's like a mix of systems. Some things look like they're best kept discrete. Some things look like they're best kept continuous. And in that sense, it's very much like the theory of zeta functions, and the whole structure of it looks very much like a kind of matrix generalization of Mellon transforms and either Hardy spaces or the I think Bargman spaces as well are very convenient. So it runs into a lot of very, very handy maths, and as I'm saying, the bulk gauges are the next. Yeah, that's the next thing to find out how to actually, for an observer within a forwards expanding bulk, it would be very nice to actually see this tiny cosmological constant, but we can kind of see it's there because the whole space is covered with patches of positive and negative curvature, and most of them are going to cancel out to a very high degree, particularly if we look down to the Planck scale. It's just going to be utterly a foam. And so that's a nice thing, is that this foamy structure works at all scales. As we can see, the photographs of the web, the cosmic web, show this. And then the nice thing is essentially kind of these models have exactly the same kind of symmetry down to all scales, particularly if we can kind of zoom in on it without the Unruh radiation. And now that is an important point, actually. Unruh, that's probably the final point, because the Unruh radiation is such an interesting phenomenon, because the effect that it can have on creation and annihilation operators, that they're no longer relative. They can change, and that can be seen as the cause of the extra modes that you get. And the Unruh radiation can essentially be seen as radiation that's crossing from one event horizon into another, caused by any accelerating frame. And basically, you can't really make stationary frames, so every frame is accelerating and jiggling around a bit. So the point is this, that how do you know if you've accelerated and then you return back to where you come from, that we haven't got some multiversal dynamics going on? And so this is a very subtle point, really, because we're really wanting for it to be a block universe without multiversal dynamics. The whole notion has been to essentially make an initial and a final observation to collapse the multiverse. And so this is an interesting point, really, about the multiverse. But I came to the conclusion that it's not necessary, because even if you don't have access directly to annihilation creation operators in the bulk, and this is an interesting thing, that okay, I've forgotten about this. This is so strange. But all right, imagine we did have bulk degrees of freedom. Then essentially they can only be bosonic, because and then we have a problem too, because we're meant to put their creation, if we put their creation annihilate, their creation operator in this space off the boundary, so not on the boundary condition in the original vacuum decay. So suppose we put any conditions anywhere else, so anywhere else in the bulk, other than on the singularity, initial singularity, then we can always trace its reverse light cone back to the initial conditions. Unless there's some way of actually saying all of them are absorbed. I mean, yes, it is possible, but it seemed to me that it's not necessary. So that we could actually, even if we, all right, so we let's suppose we can do it both ways. There's no need to fix a model here, because there are still some choices left. So we can either say, all right, we can introduce a boson creation and a boson annihilation operator within so we have to, it's essentially on the Fock space, what we've got to do is say, all right, we've got all of these conditions, that initial conditions that are on the singularity, but we could also say, all right, well, let's just kind of edit it a bit and stick some other annihilation creation operators in there. And then, okay, it makes a specification of one of these things a little more complicated, because we can't just simply think about it as a vacuum decay, because it's a kind of tailored vacuum decay where we said, all right, well, when we specified the initial conditions, there are also these special times too, where we want things to happen. And it just seems a little bit fine-tuned to me. So is there a way that we can just pull the boundary conditions right back, even with the boson? And there is. Because what we can do is, say we want a photon wave function to have an annihilation at a space-time event, and then a creation, then an annihilation at another time. Then what we can do is we actually send on, we specify it as a photino on the boundary. And then we specify a supersymmetry a supersymmetry action to, and so that photino is going to travel in a patch of negative curvature. So it's not going to be observable by any strong measurement. But then it can pop out in a nearby event horizon, because remember, the whole of everything's covered with event horizons everywhere. But not all singularity type event horizons. Some of them are membranes. And so then this thing pops out the event horizon as a boson. That boson, if it's on if it's genuinely a bosonic orbifold, then we have to either let it, if we want it to be absorbed by something, well, it can just basically be absorbed by something else, to a boson, to another fermion. But we can either keep it visible, or if we want it to vanish, we just turn it into another photino. So, and then off it goes backwards in time. So we can use negative curved spaces, so really powerful in computing terms, bus, for routing signals from the initial conditions to an event, space-time event, without actually having to specify their space-time coordinates explicitly. And then we don't need any level of fine-tuning. But it appeared, that again appeared to me today as kind of, what is supersymmetry good for? And this is one thing that it would be really good for, pushing boundary conditions to a singularity. And essentially that kind of wraps up all the information into the excitation. And I suppose that kind of wraps up this stream, really. So if anyone has, stuck through it, or well done, and hopefully I'll be able to get more on a later stream and actually see whether I've managed to make any progress with the psi plus, because that seems really mysterious, because I really think these surfaces are likely to be charged, and I want to see how to get some charge on there, given that we have no real degrees of freedom. There must be some mechanism of charging them up, but right at the moment I can't see it. So let's see. At the moment they're hypercharged. We've got a weak hypercharge, I suppose. That's pretty good, but we really want charged black holes. So let's see where it goes. Many thanks. Enjoy. Bye.